Hello and welcome to the lesson on print views. At the end of this chapter, you'll be able to interpret 2 and 3 view drawings and identify the dimension definitions for height, width, and depth. Let's begin. Blueprints come as 1, 2, or 3 view drawings. The number of views depends on the shape and complexity of the object the drawing is trying to describe. In this chapter, you will be introduced to the different views used to describe an object. And just one thing I want to highlight first, it refers here as blueprints. That's kind of an old school terminology. We're just going to refer to it as print for this lesson whenever I speak. Just real quick before I go on to the next slide, here are some examples. And we're going to be covering these 3 examples specifically. So here we have a 1-view drawing. It's only giving us 1 view. Well, here's a drawing where it's giving us 2 views. And they're nice enough to also give us what's called an isometric view. And down here is our traditional 3-view drawing. I would go as far as say easily 90% of the drawings, the prints on the shop floor at Monty Incorporated are 3-view drawings. So we're going to cover all this, but just in summary, this is your front view, you have a top view, and this would be your right side view. And up here, of course, is what's called an isometric view. Let's go into these examples further. Views. A view is the way you look at an object. It describes an object from 1, 2, 3, or many different directions. A view should not be on a drawing unless it provides information needed to describe the part clearly. Alright, this is one of the best examples I've seen in terms of being able to understand what the heck is a front view, a top view, a side view, heck, back views, bottom views, left views. So think of the part that you're manufacturing as this enormous, enormous part. And you are this person standing and walking around the part. It's so big you have to walk around it and get on a ladder and look down on it. So if you're looking at the part and you're standing in front of it, that is referred to as a front view. Looking right at it. So let's say, okay, I want to see what this part looks like from the right side. Okay, that's going to be called a right view. So you walk over here. Now you're standing in front of the right-sided view. Okay, the part stays stationary. It does not move. You are moving about the part. So if we go to the right side and you start looking at it, that is called the right side view. Then let's say you got on a ladder and you went up and you looked down on top of the part. Okay, part stays stationary. That's referred to as a top view. So whenever you're looking at a part, think of yourself as the person, and the part being enormous, and you are walking about the part. The part stays fixed. It does not move. It's isolated. 3-view drawings. Let's discuss the front view. The most common method for describing an object is to use a front, top, and right-sided view. The front view is the surface of the object as it appears when raised to eye level and turned so that only the front side can be seen. Okay, so before we were looking at this object. So if I was to extrude just what we're looking at during a front view, this is what it would look like. Okay, this represents that piece. This piece right here represents the rest of the body. So imagine the image projected by the object onto this plane creates the front view. Now let's talk about the top view. The top view is the surface of the object as it appears from directly above. The top view is always placed above and in line with the front view on the drawing. Okay. In line. Keep in mind the part does not move. The person is moving about the part. So the image projected by the object onto this plane creates the top view. Okay, so you go up on a ladder and you look down on top of the part. So you're looking down on top of it. This represents this part of it, and this represents this. If you're looking down from the top view, you can't see this surface. All you're going to see is that in this top view. Okay, the right side view. The right side view is made from the same way as the front and top views. The right side view is always placed immediately to the right and in line with the front view on the drawing. Okay, the same could be said for a left side view. Okay, but instead of being over here, you'd be over here. So if I was to walk around the part stays stationary, and I go and I'm looking at the part, all I'm going to see is this surface and this surface. So if I was to pull all of these views together and put them on one plane, one sheet of paper, what you have here is your front view, top view looking down on it, and you have your right view going over to the side, the right side that is, and looking at the part. This is what the part would look like when put on paper that's distributed to the shop floor to manufacture a product. Okay? Here we have what's called an isometric view. An isometric view is like taking the front view and pulling it over here to the upper right hand corner and giving you a 3D look at the part. Okay? So when you go at it at 45 degrees, you're always going to be looking at the front view. So 45 degrees would be your front view. This would be your right-handed view. This would be your top view. So front view, top view, side view, which would be from the right-hand side in this case. If we were to look at it a left-handed view, you'd see something that would go like that. In the last 3 pages, we have discussed views. But what if someone else who uses the same blueprint calls the front view the top? It is more important to understand the relationship between the views than the names we assign to them. In a drawing, views are always at the right angle to each other, 90 degrees. Okay, you're rotating 90 degrees about the part. So in this example, you could see it's the exact same part we've just been staring at for the last 5 minutes. But it's oriented a little bit different. Okay, but that's okay, it doesn't matter. It does not matter. So now, if I'm looking directly at the part for the front view, based on it laying on its back now, that is all I'm going to see in a front view. If I go to the top looks like the part that we were looking at previously in the front view. And the same could be said for the right view. It's just different, but it's all relative to each other. Height, width, and depth. The term height, width, and depth refer to the specific dimensions. Height is the vertical distance between two surfaces in horizontal planes. So the height is from one plane to the other plane, going up vertically, up and down. Height is vertical lines. Now, when we talk about width, that's referring to the horizontal distance between the surfaces in profile planes. The terms width and length are used interchangeably. So you could actually say, well, no, the width is about the horizontal line. No, the width should be about the vertical. Well, you're either going to have a depth and a height and a width. Lastly, we have thickness. And thickness is going from one plane to the other plane. So we have height, width, and depth. These could be used interchangeably. I know we just hit on that, but based on how you orient the part. But you always have to have a depth, width, and a height. And depth could be referred to as thickness versus depth. Two-view drawings. A part that can be fully described in two views is usually simple and the same on all sides. Parts like sleeve, shaft, rods, and studs are example of parts drawn in two views. A lot of our turned parts. So if you're working in the lathe department, that's the area you're more than likely going to see a two-view drawing. That's not so much the case in our milling and fabricating applications, as you usually need to show three views to show all the characteristics correctly. Notice that the front view always looks the same when the part is rotated 90-degree increments. So no matter how this part, if we rotate it 90 degrees, 90 degrees, 90 degrees, the view is going to be the same. This is a perfectly symmetrical part. No matter how we rotate it, it's going to be the same view. Again, this is just illustrating that when we rotate the part 90 degrees, the view is still going to be the same, because it's a symmetrical part. And again, rotating it another 90 degrees, you'll see it's the exact same view. Two-view drawings can be the front and right side view, or the front and top view of the object. Drawings with two views have the same level of detail as three-view drawings. There's just not as much detail to express, but they are expressing the full detail of the drawing. And here's one of the most simple views, and you will see these most commonly in our turret punching operations, sometimes in the dry mill on simple parts with holes in it. But one-view drawings are regularly shaped parts that can usually be described in one view. An example is a thin, flat object. Notes are used to provide detail about the thickness dimension on the part. It actually, you can't see it, but there's notes down here that describe, okay, what thickness the material needs to be. Notes supplement the dimensions on the drawing, furnishing all the needed information to accurately describe the part. So pretty basic. You could say this is a front view or a top view. When I look at this, I like to think of it as a top view, just looking down on the part, because when I'm holding a part and it's only got work being done to one plane, I usually lay it flat. So I like to think of it as a top view, but it really doesn't matter. You can consider it a front view if you like. Now here's a one-view drawing where there's work actually being done to all 6 sides. But in this case, there's only one view because it's completely symmetrical. So spheres and cube objects are good candidates for one-view drawings. Hidden lines are used to show internal and hidden detail. So as you can see, it has the hidden lines through here. This hidden line going vertically expresses this hole. This hole right here, this hidden line, sorry, going horizontally represents this hole right here. This hole right here is a solid line because it's representing this hole, which we're looking at directly. Sometimes even simple objects like cubes need multiple view drawings. A dice is a simple cube. The detail on each side of the dice is different. Sorry about that. 6 views are needed to fully describe a die. The number of views needed to describe an object changes with the complexity of the object. So we have to show actually here 6 different views because each side of the dice has a different number of dots. So again, here's your front view corresponding with the isometric view. Okay, going at a 45-degree angle. That's your front view. And we're stand on top of the dice. I see 2 holes. Well, if you stand over here, see 2 holes. If you go to the right-hand view, right side view, walk over to the side of the dice, that's the view you're going to see. If you go behind the dice, now you can't see that in this isometric view, but if you were to stand behind the dice, you'd see 4 dots. If you go to the left side of the dice, you'd see the 1 dot. And if you were to crawl underneath the die and look up at it, you'd see the 5 dots. Okay. Lastly, one thing we need to discuss are sectional views. A sectional view is used to see internal detail of a part. Hidden lines can describe some internal detail. We use a sectional view for internal detail that cannot be clearly described by hidden lines. So what we got here, if you notice, we've got the red highlight here. This is a cutting plane. So let's pretend we took a knife and we have this part laying on the table and we could just slice right through it. Now see how the arrows are going in this direction? That's the direction at which we're going to look at the part. So if I was to cut this in half, I would throw this bottom piece away and only keep this piece, and I would want to look at the section that I just cut away, which would be this. So if we threw this away, rotated it up 90 degrees, this is what we would see. And this is referred to as a section view. Here's another example of a section view. We kind of just discussed this one. This is a round part that we've cut in half. Well, this is a little bit different. This is like a piece of a detailed drawing with just a little section. So the sectional view is obtained by passing an imaginary cutting plane through the object. The portion of the object between the cutting plane and the sectional view is assumed to be removed. The exposed surface of the object is drawn with the cross-section lines at 45-degree angles. That's one thing I forgot to point out up here. See how it's got those 45-degree angles in there? That's indicating, hey, look, this is an internal view of the part. It's not an external looking about it like we've been talking on the underviews. It's a slice of the part. So we take our knife and we slice it right here in what looks to be a handle or something like that. We take a slice of it there. We're going to throw this section away, and I'm going to look at it going this direction. And here is that section view. Again, it's got the 45-degree lines indicating that it's a section view. And your prints will say section view A. See how it says A here? A here. There might be drawings. Well, there's definitely drawings out there where there might be section view A, section view B, section view C. There could be many different section views on the drawing, but the A corresponds to section view A for the cutting plane. Okay, in summary, we have explored the different views used to describe a part. We learned to visualize a part using a three-dimensional drawing, and we understand how the relationships between the views on the drawing are more important than what we call the views. Okay, so just remember, the part stays stationary. You, the person, rotate about the part, looking at a front view, side view, and top view. Let's take the test. Good luck. Thank you.